Okay, this is video number 2 of day 4, and we had just been talking about water as a good solvent. Next, we will be getting a little bit into acidic versus basic conditions. Things out there in the environment are often very susceptible to acidic or basic conditions. Some of you may have heard of acid rain before, or you may know about some of the chemicals in your cleaning supplies cabinet that may have basic or acidic properties to them. So let's look a little bit at those. When something is considered acidic or basic, you see that if it is considered acidic, it is going to have hydrogen ions, and if it's considered to be basic, it's going to have hydroxide ions. So when we look at something like water, water is usually like the picture on the right, which has the oxygen with the 2 hydrogens coming off of it. But at any point, one of those hydrogens can break off and leave behind an OH minus or hydroxide ion, and so that gives it a charge to it. So the pH scale is going to be the amount of H plus or hydrogen ion in a solution, and then the measure of bases is going to be the OH minus or the hydroxide ions in a solution. So if something is considered very acidic, it's going to have a greater proportion of H plus ions to OH minus. So if you look here at this little picture right here, we've got all these little H pluses hanging around. Those would be the H plus ions. They are very reactive. If it is a strong acid, it can actually be corrosive to metals. Acids break down your food in your digestive system, and they generally have a sour taste to them. So if you look here at the middle of our pH scale, right there at the number 7 is the pH of water, and water is neutral. And then as you start to get into 6 and 5, we start to get into coffees. Then we start to Oops, did I go the wrong direction? Oh no, I'm going the right direction. And then we've got beer is more acidic than coffee, soda is more acidic than beer, and then finally we get to things like battery acid. You can also think of like lemon juice. If you look down at the little bubble right here, that's very interesting. Soda with a pH of about 3.0 is 10,000 times more acidic than a glass of water with a pH of 7. If you look here at things that are more basic, we've got blood is coming in at right about a 7.3. We've got baking soda, which can be used to cook with or used to clean with. Ammonia is another strong cleaner. Then we get to bleach, which is really basic. And those are going to have more of the OH minus ions or the hydroxide ions that are floating around in the system. They are used to neutralize acid. If you remember back to the scene from Fight Club where he puts the lye on the other guy's hand and it starts burning into his hand, and then eventually he has to neutralize that. Those are an example of very strong bases and very strong acids that are neutralizing them. Strong bases are caustic to your skin, so that would be what lye is. It would be a caustic base. And bases can be found in lots of different household cleaners, and they are generally bitter to the taste and kind of soapy. So that's why they are such good cleaners. H plus ions and acids, like we just looked at, they're very reactive. Acids donate H pluses to other chemicals, and one of the best examples in our human body is stomach acids. Then bases have a low amount of hydrogen ions and a high amount of hydroxide ions. These would be things that, like what we put into our body, would be antacids, like milk of magnesia, talking a little bit about like your Tums, then things like baking soda and seltzer, so things that kind of balance everything out. One of the most interesting things about how we are able to survive is the fact that our blood acts as a buffer and helps to stabilize our systems. So where we have lots of acids that are in our stomachs, we have our blood, which is more a little bit on the basics side, and it acts as a buffer. So something that's a buffer can quickly absorb excess hydrogen ions to keep them keep a solution from becoming too acidic, and they can quickly release hydrogen ions to counteract any increases in OH minus or hydroxide concentration. So up here you can see when your blood pH level becomes too acidic, then buffer chemicals absorb those H plus ions to bring your blood back down to normal. So we've got all kinds of different buffers in our blood that helps to keep it stable, because your body doesn't want to swing too high or too low, or you'll become sick, and in extreme cases you can actually die from that. So now moving from a whole separate topic, we had just talked about acids and bases and talking a little bit about chemistry. Now we move into the different macromolecules that are really these building blocks of your body. So one of the first ones we are going to look at is carbohydrates, and carbohydrates serve as a fuel for living machines, basically this energy for your body. So carbohydrates include macromolecules that function as food. Some of them may interest you because you may have heard of things like low-carb diets, high-carb diets, carbo loading. Some of you may have heard that you should increase your fiber intake if you don't want to, if you want to help to feel full faster. So one of those questions is, what are these carbohydrates in the first place? The four different types of macromolecules that we're going to talk about in this section, besides carbohydrates, are lipids, proteins, and nucleic acids, kind of these building blocks of your foods and of your body. Carbohydrates are only going to have the elements carbon, hydrogen, and oxygen in them. Here you can see those three elements. You can see the way that they're all shaped together in order to make a long chain, like this is an example of glucose, which is C6H12O6, which means it has 6 carbon atoms to every 12 hydrogen atoms to every 6 oxygen atoms. And when those bonds are broken, that's when energy is released. And in carbohydrates, we see an extreme amount of energy being released. And so those are broken down by organisms. And this here, this little green symbol, is the symbol for glucose that's used in this book. So carbohydrates are basically the primary fuel for your cells to get their energy from. And so it's this fuel, and it's helpful in building blocks or becoming the building blocks of your cell structure. So the energy that we get from our foods is actually found in the chemical bonds and isn't released until those bonds are broken. Glucose provides energy for the body's cells, provides fuel for all those cellular activities. It's temporarily stored as glycogen, which is something that is stored in your liver and released as it's needed. And if you have too much of it, if you eat too many carbohydrates, it can actually be converted to fat within your body, and that's what can eventually build up and start to cause some health problems. Glucose is ultimately what most carbohydrates that you eat are converted into, and this is what goes to make up your blood sugar, which is the amount of sugar in your blood that can be used for energy. So some of those things that we see when you have glucose in your blood, 3 things can happen. If your body needs that energy, then the molecules are broken down by your cells and release the energy, and you can run and jump and do all the exciting things that you need to do. However, if that energy is not needed, like if if you go and start eating right before you go to bed, the energy will either be stored in your liver as glycogen, or in the long term it can be converted into fat cells. And so you may have heard of athletes before they go on a long run or before they go on a bike ride or a triathlon, that they may do something called carbo loading, and that's when they eat a huge amount of complex carbohydrates to store that glycogen in their muscles and in their liver, and have it be available to be extended as energy used for bicycling or running or whatever it is. And so you may have heard of athletes having a big plate of spaghetti before they go out. That helps to give them the endurance that they need in order to run the race. And so why do dieters lose large amounts of water weight during their first few days of a diet? This is what a glycogen molecule looks like, and often the very thing that's stored on the outside of that glycogen molecule is water molecules. And it says for every ounce of stored glycogen, you can have as much as 4 ounces of water bound to it. So as you go about trying to diet, those water molecules are released and expended from your body before the energy is ever going to be released. So some of the weight that you can lose, even it seems like overnight, sometimes you may go to bed and have one weight and wake up in the morning and be a few pounds lighter. Because that water is being expended by your body, not because you're actually losing any fat. Many complex carbohydrates are time-released packets of energy. So we have sugars, sometimes called monosaccharides. So if it is one sugar, it's called a monosaccharide. If it has a more complex sugar, disaccharides mean 2 sugars like sucrose and lactose. Lactose you probably should recognize because it's the sugar found in milks. And then polysaccharides are these complex carbohydrates. These are our starches or our cellulose. And so in something like starch, we can have hundreds of glucose molecules joined together. And so starches would be things that are complex that you may have heard about in your cereals, that you may have heard about in your pastas, things like barley and wheat and rye and corn and rice, some of the bases or staples of our food supply. And then we have things that are called glycogen, and that's what animals store as starch. And so we'll move on to the next video here in just a minute.